So recall in chapter 7, right, we have the central limit theorem, right, which states that if we have a large enough sample size, then our sample distribution, meaning our sample mean, will have a normal distribution. Now that is partially true. That's true, right? If we have the population standard deviation, okay, so that is a sigma. So if we have sigma, then yes, we can clearly make that statement, and we can use the normal distribution directly to estimate the distribution of x bar. Right? However, right, if we don't have sigma, okay, then if we don't have sigma, then x bar, it is still distributed semi-normally with mu in the middle, the standard error of x bar. It is still sigma over xn. Now the sigma over root n. Now the only difference is I can't use sigma because I don't know sigma, so I would need to use s, the sample standard deviation, in place of sigma. Okay, but it is still s over root n. Okay, now the shape here is not going to be exactly normal anymore. Okay, but instead it's going to be following a t distribution. Now a t distribution has a very similar shape. Okay, has a very similar shape, and it is approximately normal. And the way we'll all right, and so the way we'll deal with t distribution is going to be very similar to the way we deal with the normal distribution. It is going to be a bell-shaped curve. It has two tails. It is symmetric. Right? And so nothing much has changed. It's just a different distribution, and we just have to be aware that, as you know, when we don't have sigma, right, then we will have to use a t distribution. Now with a t distribution, we have to calculate what is called the degree of freedom. Okay, don't worry about what it is. The calculation is very simple. Right, a degree of freedom. Right, so the degree of freedom simply equals n minus 1, right, for our sample mean. Okay, so whenever you want to calculate the degree of freedom, you just take the sample size, you minus 1. Now, how does the degree of freedom affect the t distribution, and why do we need the degree of freedom? Right, because when we are using the normal distribution, we never talk about degree of freedom. Well, that is because the degree of freedom actually affects the t distribution itself. So I'll give you two examples. Right? So one, so if let's say that I have a degree of freedom equals 5, for example, then the t distribution will look probably something like this. Okay, not that peaky, right? The peak is not that high, it's kind of flat. However, if the degree of freedom, let's say, equals 15, okay, and now, right, now it becomes closer to a normal distribution. Right? And in fact, as the degree of freedom gets higher and higher, the t distribution becomes closer and closer to a normal distribution. Okay, now I understand this might seem a little bit confusing, but really, the way again, the nothing much has changed in how we will deal with t distribution versus normal distribution. Right, we just have to be aware there's an extra parameter, the degree of freedom, and know when to use it. And in that case, that would be when we don't know what sigma is. Okay, now we're ready to find the critical value. Okay. All right. So finding the critical value is the first step in constructing a confidence interval, because we need it for our margin of error. Right? Because remember our margin of error formula here, it is E equals critical value times the standard error of x bar. So we need to find the critical value first. So to get critical value, first we need to determine the critical level. Now the critical level is Oh, wait, hold on a second. Sorry. Okay. Now, the critical level is chosen by the researcher. So you're either told what you like the critical level to be, right? And so this is determined. This is not something that we measure. Critical level is a choice, right? And so we'll choose. So critical level will again is 1 minus alpha times 100%. So critical level will always express that in terms of percentage. And again, alpha is this critical, or all right, alpha is called the critical level. Okay. Okay. Oh, sorry. I mean the confidence level. Right. So confidence level is 1 minus alpha times 100%. Right. And alpha is this critical level. Right. And we'll discuss later what alpha really means. But right now, let's just focus here. Okay. So for example, right. Examples. Right. So if alpha equals, let's say, 0.10. Okay. Then 1 minus alpha will equal 0.90. Then that means our confidence level will be 90%. Right? It's 1 minus alpha times 100 times 100%. Right? If alpha equals 0.02, okay, then we can go a little bit quicker here. Then that means our right, confidence level, right, will be not critical level, confidence level, right, will equal 98%. Okay. All right. Now, once you have the confidence level, or you understand the confidence level, right? We can know, what now we can know what critical. We can locate our critical value. Okay. So whenever we look up critical value, we need to first be aware. Do we know sigma? Okay, if we know sigma, then we use the z distribution. That's the standard normal. If we don't know sigma, then we use the t distribution. Okay, but in either way, right, our critical level will indicate our critical level is the number that will give us, right, our critical value. Sorry, I keep saying critical level. Our critical value, right, is these two numbers. Okay, and the area, it's symmetric, or at least I try to draw it symmetric here, right? And what is this area? That area is alpha half. So we take alpha, the critical level, and divide it by 2. And in the middle here, that's our confidence level. Okay, so our confidence level is the area in the middle. Okay, and so for example, right, if alpha is, let's say alpha equals 0.10, right, then alpha half equals 0.05, right? And so we know what the area in the tail is, and the critical value is simply the number that will give us the area in the tail. Okay, we'll do an example in just a moment. Okay, but right now I want you to just have a visual of what a critical value is. And so when we use the z distribution, the critical value, we will use this notation, z alpha half. Right? Okay. Now, when sigma is unknown, we use the t distribution. But the picture will look exactly the same. Right? We will we will take alpha, our critical level, right, divided by 2. We will allocate the area in these tails, and the critical value will still be these numbers, this number here. Okay, and that will indicate that with t of alpha over 2, right? That's going to be our critical value. So this is a critical value of t, and this is the z critical value. Okay, so I think it will become a little bit clearer when we do a couple of examples here. So let's find the critical value z given alpha. So if we're saying that we're gonna look for the z critical value, that means we know sigma. So this means sigma is known. Okay, don't worry about how we know it, right? Either the problem will tell you that we have sigma, or we're gonna assume that we know sigma. Okay, so alpha equals 0.2. All right, so we got alpha. Okay, so that means we got here. That means we split up alpha. Alpha is always in terms of area. So alpha half is going to equal 0.2 divided by 2 will be 0.10. Okay, our critical value is the number that will give us a tail of 0.10. Okay, now we can use our app to figure that out. So we will use, okay, now here's the important part. We know sigma. We're using the z distribution. So that tells me that I need to go to normal. I am using the normal distribution. Okay. Now remember, the z distribution is just the standard normal. That means the mu is 0 and the sigma equals 1. Okay, now I got that. Now I don't know x because that is a critical value. That's the number that I'm looking for. But instead, I know what the area to the right is. The area to the right of the tail is the right tail is 0.10. Okay, so I put the area in, and then once I hit check, it's gonna tell me what the number is. Okay, this is 1.28, and that's my critical value. It is my critical value equals 1.28. That's 1.282 there. Okay. And again, I got it from that. Right. Alternatively, right, we could also find it using the normal distribution or standard normal distribution table that is available in the folder or in the back of your textbook. Now, to do that, right, I will need to look inside here, inside the table, to find an area of 0.10. Right? And then find the corresponding find the corresponding z value that goes with it. Okay, so here I can see that here I get 0.10. Okay, you see this is over here, and that gives me 1.2 and go up 1.28, which is exactly what we got. And actually the app is actually more accurate, right? This because this table only goes to 2 decimal places in terms of z-score. Now, one of the good thing about this table is, however, is that because we use CERN alpha so often, right? That we have a nice table here that is very convenient. So if we just say, okay, well, alpha is 0.2, as in our example, then the z-score is 1.28. Okay, so it's right here. So you don't have to go inside the table to hunt for 0.10. You can just read it here, just as long as you know what alpha is. Okay, and this gives you a nice picture of where the critical value is corresponding to the what alpha is and what the tail is. But you're free to use either way. Use the app or use the table. Okay, so go ahead and give that one a try, and then if you want, you can feel free to pause the video and check your answer when you're done. Okay, so again, I suggest always sketch, right? Always sketch so you make less mistakes. Here we go. I need those two tails. My alpha at half now, in this case, will be 0.025 divided by 2. That's my critical value. I'm going to use the app to figure out what that is. So the only thing I'm changing here is my area, 0.025, and hit enter. Okay, so my z alpha half, my critical value is 1.959. I'm just gonna say 1.96. Okay, now moving on to finding this. So if I find the critical value t, okay, also now I'm saying, okay, I need to use the t distribution. So that means my sigma is unknown. Okay, so somehow I don't know, for whatever reason, I don't know sigma. And actually, this is going to be the case most of the time, because most of the time, we don't know sigma. Okay, so if we don't know sigma, then we need to taking into account the sample size. So again, same thing here. I have alpha equals 0.2. My shape is going to be the same, so I can go ahead and just do a sketch to help guide me. Okay, and here is my t alpha at half. My tail is going to be divided by 2 is still going to be 0.10. However, I need to calculate my degree of freedom. So my degree of freedom is 5 minus 1, so equals 4. My degree of freedom equals 4. Now, how do I find the critical value? Okay, I highly suggest using the app because this is far more accurate than the table. Okay, so I am no longer using normal distribution, so I need to go change it into a t distribution, right? Because I don't know sigma, so I am approximating I am approximating the normal distribution. This v here, right, is actually nu, it's not v, but anyway, is this v looking thing? That is where you put in the degree of freedom. So you put in the degree of freedom of 4. And then, I don't know x, that's what I'm looking for, but I do know the tail, and the tail I want is 0.10, or the area, I know that the area in the tail, 0.10, and hit enter, and voila, there we go. So that's my critical value. Okay. Okay. Let's go ahead and try to give this one a try. Pause if you like. For part B. Okay. Again, so always sketch. Right. You make less mistakes this way. Alpha half. 0.05. My n equals 11, so my degree of freedom equals 10. Okay, so all I have to do on my app is to change the degree of freedom into 10, and then change it to 0.05. Enter. Okay, my t alpha half equals 1.81, 1.1, oops, 1.3, yes, 1.3. I'm just going to round to 3 decimal places. Okay, and so that's it for critical value.